Okay, hi, welcome to Group 17's Concrete Strength Model Analysis presentation for Stat 512. So the data set that we have chosen is a data set from China that looks at the different components of a concrete recipe and gives a compressive strength of the concrete of the recipe on a specific day after mixing. Concrete's a very unique building material in the fact that it's made and poured on the job site and must follow specific recipes, which will change the characteristics of the concrete. We've decided to determine how different recipe components can affect the concrete mixture in a variety of ways. So the variables of our data set include the cement content, the blast furnace slag content, the fly ash content, which we have turned into a categorical variable for one of our questions, the water content, the superplasticizer content, the coarse aggregate content, the fine aggregate content, and then age, which we've also turned into a categorical variable.
Hello, my name is Danish Suhail, and I'm going to be talking about my research question, which is about investigating the linear impacts of water superplasticizing and blast furnace slag dependent on whether or not a mixture contains something called fly ash, which is a recycled byproduct material. And so my hypothesis expresses this. We're interested in observing that these interactions are present. And so for my data cleaning process, I didn't really need to clean very much. I just needed to create a new column in R, which was dependent on whether or not a particular mixture actually contained fly ash. So if it had zero fly ash, it would be false. Otherwise, it would be true. And so for my exploration, I used box plots. Here we see the compressive strength and water quantity box plot and superplasticizer and blast furnace box plot. However, superplasticizer these and blast furnace both had many mixtures that contain zero quantities of these materials. So I then conditioned on looking at box plots which for materials and mixtures that contained at least some amount of these ingredients. And so superplasticizer notably has a lot of outliers in this case. So I used a histogram to further investigate it for any bimodal behavior. And it looks like this. We see a strong skew to the right. Here we have three residual plots for the three main linear impacts we're interested in. So blast furnace slag, superplasticizer, and water. And then we also have QQ plots for concrete strength relative to how much fly ash is contained for fly ash containing mixtures. And then we're also just comparing the strength between both groups in these two box plots here. So here I have some simple ANOVA analysis using the three basic continuous variables that I utilized, and then also observing these three individual variables, doing some SLR analysis, as well as looking for some degree of marginal reductions. And for my Cook's tables, we see this. I did not see any particular behaviors, even though we do have large bubbles. They are evenly distributed around the zero line. So I thought that it was okay to use. I computed the VIF and mainly noticed multicollinearity between the water and the superplasticizer variables. However, blast furnace slag presented almost no multicollinearity behaviors. And here's the full models in R for containing fly ash and does not contain fly ash. And then I utilized a stepwise regression method. So here with the stepwise regression method, I slowly pared down variables, optimizing for the AIC. And so I tried a couple of these simpler models and then also ended up converging on this model here, which ended up being what I rolled out here at the top. Notably, both of these boxes are one is applied, the top left is applied to the fly ash containing group, and the bottom right is to the non-fly ash group. So then I applied a simple cross validation technique, k-fold, and then a working hoteling confidence intervals. So ultimately, what I realized was that of the interactions that ended up in my final model, I can't really say whether or not it's really hard for me to say that these interactions really do exist, and as a result, I found it really difficult to reject the null hypothesis. However, more investigation would be needed. Thank you. I'll pass it on to my teammate now.
So I'm Craig Ryan, and my research question was, does concrete or water content change the effect on compressive strength before, during, and after the concrete standard curing age of 28 days? So my variables include cement content, water content, and the age, which I turned into a categorical variable, including beta 9 and beta 10. And the reason for this is because the data set that we got, the age of concrete was already essentially a categorical variable, with concrete being sorted into essentially 7 days, 14 days, 28 days, etc. I simply grouped it into the before 28 days, and the after 28 days. And this is due to 28 days being the standard amount of time for concrete to be considered at its final strength. So for my null hypothesis, there are no interactions between water and age nor cement and age, essentially meaning that neither water nor cement contents will change the rate at which concrete hardens. You can see my reduced model here. My alternative hypothesis is that there are interactions between water and age or cement and age, meaning that either water or cement content will affect the rate at which concrete hardens. And you can see my full model there. So for data exploration, I started out by looking at a residuals plot of my model, which appears to be a relatively healthy looking residuals plot. And the Shapiro test confirms that it is a normal distribution. And the Brush-Pagan test will actually show that there's a high level of non-constant variance with a very, very significant p-value of 3.87 times 10 to the negative 7. So I also found that there's no significant multi-collinearity between the main effects of cement and water as shown by the matrix as well as by the VIF. And I ran the influence plot, which includes the DFITS data and Cook's distance. And you can see in the influence plot that there are some highly influential points, but due to the size of the data set and where it's concentrated, I'm not terribly concerned by these influential points. For remedial measures, due to the lack of multi-collinearity, I did not remove any predictors right off the bat from the model. And the weighted least squares, I ended up using a weighted least squares model to correct for the non-constant variance as well as assist with those influential points. And you can see that it remains normal, and the Brush-Pagan value, p-value, has become a much more healthy 0.9, which means that it is now it now has constant variance. And you can see in the influence plot in the bottom right corner that there are significantly less highly influential points, and the points that are highly influential are significantly less so, which is great. For the validation, I used a k-fold cross-validation with 10 folds, and it returned a low R-squared of 0.67 and a root mean squared error of 9.63. This may be slightly overfit. This model might not be perfect, but it is a completely usable model. So I ended up using the Bonferroni simultaneous confidence interval to test the significance of the different interactions. And the two interactions that yielded to be the most significant are cement times the age at 28 days and water times the age at 28 days. Cement times age being negative and water times age being positive. All of the insignificant ones are either lower order terms of significant terms, or they are members of the age, which is, of course, a categorical variable. So they are not droppable. So this model shows that the cement content will harden a concrete faster at a faster rate before 28 days, as shown by the negative at 28 days, while more water will harden the concrete more quickly at 28 days. So this essentially shows that concrete will take longer to dry out with water, and it will harden more slowly, therefore taking longer to gain its strength.
For my portion of the Stat 512 project, I aim to answer the question, does water content have a significant impact on compression strength when combined with other important concrete ingredients? To this end, I selected a couple important variables for my model. These include the variables on the left, which are directly from the dataset, with the exception of fly ash, which was turned into a qualitative variable with 0 denoting no fly ash in the mixture and 1 denoting fly ash in the mixture, and the addition of 3 interaction terms, namely water slag interaction, water superplasticizer interaction, and water cement amount interaction. When creating my model, I ran into some problems with assumptions. First of all, variable selection and model selection was done primarily with the research question in mind and not through a robust statistical method. This was done through the choosing of interaction terms, the inclusion of water quantity, as well as the inclusion of different concrete ingredients as concluded by a thorough literature review. My initial ordinary least squares model with all these variables, however, did not meet assumptions, with a Bruce-Pagan test of 1 to 1.27 and a low p-value indicating non-constant variance in the model. To this end, I tried several remedial methods to try to meet this assumption. The first thing I tried was a log transform, which marginally improved the Bruce-Pagan statistic. The second was a Box-Cox transform, which again improved the statistic slightly. To this end, I used a more powerful method in weighted least squares. This helped me meet the constant variance assumption with a Bruce-Pagan statistic of 0.048239 and a p-value of 1, failing to reject the null hypothesis that the model has constant variance. Importantly, this also met normality assumptions, as our Shapiro test produced a test statistic of 0.99636 and a p-value of 0.01681, meaning that we again failed to reject the null hypothesis that our model is normally distributed. Lastly, when it comes to addressing k-fold cross-validation, I did k-fold cross-validation with 5 folds and saw an increase or a decrease in RMSE by about 0.1. This means that from our first model to our last model, we saw an increase in predictive power of our model, which is always a good thing. On the bottom here, you can see the equation for our model, and on the right, you can see a graph of residuals versus fitted values, showing that our model meets variance and normality assumptions. When it comes to multicollinearity and outliers, we were expecting issues with our interaction terms, and that is what we observed. As you can see in the table, we observed extremely high VIF values for our interaction terms. Like we said earlier, during data exploration, these interaction terms were found to have high correlation with water content and the ingredient that the interaction term was made up with. However, we made the decision not to drop any of these predictors as we found them especially essential when it comes to answering the research question. Also, we used DFF-ITS to find outliers and influential points, of which we identified 58, but again, we did not drop them out of fear of introducing bias into our model. Again, in model validation, you can see the marginal p-values of all of our predictors are extremely statistically significant, except for superplasticizers or water interaction, which is a touch over 0.05. However, the model as a whole is still significant. Next, to answer the question of the day, we use a working hoteling simultaneous confidence interval to answer these hypotheses on the 3 interaction terms. You can see here our working hoteling test statistic and the conclusion we reached on the right, where we rejected the first interaction of slag and water, we failed to reject the second interaction of superplasticizer and water, and we rejected the third of cement quantity and water. You can see here how we reach those conclusions, as the slag water interaction and the cement water interaction both do not contain 0 in their confidence intervals, whereas the superplasticizer water interaction does, meaning that the true population value of this parameter might be equal to 0, and therefore it might be insignificant when it comes to the model.
Hi, I'm Krish, and my research question was, what is the optimal combination of cement and aggregate content to maximize compressive strength in concrete? So I had 2 hypotheses. The first hypothesis was there is no interaction or combined effect of cement content and aggregate content. And the alternate hypothesis is that interaction between these variables significantly impact compressive strength. So to test these hypotheses, I modeled the relationships using interaction terms to evaluate if they provided additional explanatory power. So first I started with some data exploration and model refining. I did an ANOVA test, a Shapiro-Wilk test, and a BP test on my models. The ANOVA test gave me a p-value of 0.0000149, which is significantly less than the 0.05 value, confirming that adding interaction terms significantly improved the model's ability to explain compressive strain. The Shapiro-Wilk test showed residuals were not normally distributed, so I applied a log transformation to the response variable. However, still perfect normality wasn't achieved. It got closer to normality, which was good for the test. And the BP test revealed heteroscedasticity, prompting the use of weighted least squares regression to address it, which I will show later on. And then once I applied the weighted least squares regression, these are the results in the graph. As you can see, the residual versus fitted plot shows improved homoscedasticity, and the QQ plot suggests a closer alignment with normality. The adjusted R-square value of 0.2477 indicated that the model explains substantial portion of the variance in compressive strength, considering complexities of real-world concrete mixtures. Next, I addressed the multicollinearity. I did the variance inflation factor values for predictors like cement and interaction terms, and as you can see, they were very excessively high. So I applied principal component analysis to the data, and then as you can see, the PC reduced the dimensionality of predictors while retaining approximately 78.15% of the variance with just the first two components. And the regression model using these principal components demonstrated statistically significant contributions to explaining compressive strength, as shown by the p-values of PC1 and PC2. And these are the results of the test after the PCA transformation. Both p-values decreased significantly. So, and also the residual versus fitted plot showed improved behavior. This step ensured that the model was robust and better suited to identify the optimal predictor combination. And then to find the answer to my question, I performed a response surface analysis. I first fit a quadratic model. And using the quadratic regression model, I generated predictions across the grid of cement, coarse aggregate, and fine aggregate values. And the optimal combination to maximize compressive strength I got was cement of 540 units, coarse aggregate of 801 units, and fine aggregate of 992.6 units. This combination corresponded to a predicted log transform compressive strength of 4.215. So to conclude, my analysis showed that the optimal combination of cement, coarse aggregate, and fine aggregate content can significantly impact concrete compressive strength by leveraging interaction terms, transformations, WS regression, and PCA. I developed a robust model to answer the research question.